All right, so now that we've been introduced to the density of states in terms of energy, we derived that over here. Let's make sure that we really understand the density of states. So this should be fairly easy, but I still want to just go over it to make sure we are all on the same page. So we're trying to understand the density of states in terms of energy. In other words, G of epsilon. That's what we want to understand. So as a very simple example, let's take a discrete density of states. So consider this discrete G of epsilon. So this is a completely made up example. So suppose there are uh, three energy levels, uh, epsilon 1, epsilon 2, epsilon 3. And I previously would have referred to these using n's, n1, n2, and n3, and would have said that n1 has the energy epsilon 1 and so on. I don't want to talk about n's anymore. I just want to do everything in terms of epsilons. So these three energy levels, epsilon 1, epsilon 2, epsilon 3, could be degenerate. So there might be five energy levels, five states that have the same energy epsilon 1, seven states that have the same energy epsilon 2, and so on. How would I express these degeneracies? That is what the G of epsilon does. So in this discrete case, G of epsilon 1, G of epsilon in general would tell me how many states there are with having the exact energy epsilon, because we are talking about discrete energies here. So it's fine with something being exactly equal to a particular value, epsilon being exactly equal to a particular value. In our made up example here, suppose G of epsilon 1, and I'll just take simple numbers, is 2. And let's say G of epsilon 2 is a 3, 4 or something, and G of epsilon 3 is 1, something like that. Completely made up numbers here. So what that means is that there are two states with energy epsilon 1, four states with energy epsilon 2, and so on. Now, we also have a distribution function f expressed in terms of epsilon, right? Typically, this distribution function is a function of mu, epsilon, mu, and tau, because it's, just think about the Bose-Einstein or Fermi-Dirac or classical distributions. So what does this f tell us? So f of epsilon, just imagine the mu and tau are fixed. So f of epsilon tells us what is the average number of particles I can find in a state with energy epsilon, right? So let's make up some numbers here as well. Suppose f of epsilon 1, if you plug in epsilon 1 into the formula for f, you get 3. F of epsilon 2, you get 1. And f of epsilon 3 may be also 1. So that means for the energy level epsilon 1, we know that there are two states. Looking at the G, there are two states that have the energy epsilon 1, and on an average, each of those states has 3 particles in it. So that's what it is. For epsilon 2, the energy level epsilon 2, there are 4 states which have the same energy epsilon 2, and on an average, each of those states has 1 particle in it, and so on. So now I can do some very simple bookkeeping. So I can find the total number of particles. Find the total number of particles in this discrete case. So how would we do that? We have all the information we need over here. So for any let's just write it out in long form. So starting with the energy level epsilon 1, there are two states. So there's G of epsilon 1, or two states, and each state on an average has 3 particles. So how many particles do I have at energy level epsilon 1? It's just going to be f of epsilon 1, G of epsilon 1, right? And then I'd do the same thing for energy level 2. Just make sure that you really understand this. So for energy level 2, or epsilon, energy level epsilon 2, there are 4 states. On an average, each state has 1 particle in it. And so that means at this energy level, there are g of epsilon 2, which is 4, multiplied by f of epsilon 2, which is 1. And similarly, the number of particles at energy level 3 would be g of epsilon 3 times f of epsilon 3. All right, and so the sum of these is the total number of particles. In other words, summation I, g of epsilon, f of epsilon I, and g of epsilon I would be the total number of particles. Okay, so hopefully that's clear. What about the total energy? So how would I find that? So to find the total energy, maybe I'll do it over here so we can keep this in view. So to find the total energy, I just need to know at each energy level, I need to know how many particles I have total. So at energy level epsilon 1, there are 6 particles total, right? And each particle has energy epsilon 1. So it's going to be g of epsilon 1, f of epsilon 1. That tells me how many particles there are with this energy epsilon 1. And so if I multiply that by epsilon 1, that gives me the total energy of all particles at energy level epsilon 1, and plus g of epsilon 2, blah, 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 epsilon 2, f of epsilon 2, epsilon 2, plus the same thing for epsilon 3. So that means the total energy would be the total energy U. I'll just write U here. What is that going to be? Sum over all I, epsilon I, g of epsilon I, f of epsilon I. So these are the expressions for the total energy and the total number of particles in this completely made up discrete distribution. Now, what if we have a continuous distribution? So if the energy levels, if the epsilons are continuous, which means that the difference between these successive levels is negligible, so it's a continuum. So for continuous energy levels, how do these things change? Energy levels. And that's usually the case in many applications. The energy levels are so closely spaced that they almost form a continuum. So you can easily extend these formulas, come up with continuous versions of these formulas. So see if you can write down the formula for n that would apply if the energy levels were continuous. Here is the answer. I'll write it first and then we'll try to parse it. D of epsilon, g of epsilon. You know what that means. Forget about the integral first. Just look at g of epsilon, d epsilon, g of epsilon. And then I have to multiply that by f of epsilon. Right? Okay. And this would have to be integrated. Since epsilon will go over all values from 0 to infinity, or in principle it could go from 0 to infinity, this would have to be integrated from 0 to infinity. Let's see if we can physically make sense of this formula. G of epsilon d epsilon is the number of particles, a number of states whose energy lies between epsilon and epsilon plus d epsilon, right? So that's the legal way of saying number of states at energy epsilon. For continuous, we cannot say the number of states that have the energy epsilon. We cannot say that. We are not allowed to say that, though that's really what we mean. So we say the number of states whose energy lies between epsilon and epsilon plus d epsilon. So that's what this is, and you know that already. And f of epsilon, as you also know, is the average number of particles in a state whose energy lies between epsilon and epsilon plus d epsilon. That makes sense? So if I want to find all the particles that lie that have energies between epsilon and epsilon plus d epsilon, it would be just d epsilon g of epsilon multiplied by f of epsilon. And then if I sum over all the energies, all possible values of epsilon, as I did in the discrete case, I'll get the total number of particles. So please pause the video and make sure that this is clear. And once you understand this, you can easily write down the formula for the energy. If the energy levels are continuous, it would just be the same idea, 0 to epsilon, 0 to infinity, d epsilon, g of epsilon, f of epsilon, and multiplied by epsilon. So this is the total energy. All right. Okay. Now,